So I'm predicting that we're going to have something that looks like this. However, how do we know that that's going to be the case? We want to try to convince ourselves based on the properties of the circle more than just looking at some numbers. Okay, so I went ahead and cleared the workspace so that it would be easier for us to work with this formula because I know it's going to be a long one. So I want to convince myself that I actually that this fourth constant difference is going to be true. And basically what that means is that the number that I'm adding to my previous amount, so the amount that I'm adding to get to the next one, needs to be cubic, because that is the same thing as having that fourth constant difference. So it's basically like if I have something quadratic, then that means I'm adding a linear term. If I have something that's cubic, I'm adding a quadratic term. So if I have something that is quartic, that means I'm adding a cubic amount to my previous number. So the number of regions, we're going to call that f of n. The number of regions f of n is equal to the previous number of regions plus something. How can we describe what we're adding every time? Well, basically, what I'm adding every time is these formulas, which depend on the adjacentness of our points. So when I was on, for example, 5 points, I needed to know that there was one that is 1 adjacent to our newest point. There's 2 of those. And there were 2 that were 2 away from our newest point. So when I drew my circle, I had my new point. There were 4 points that were already there. There were 2 that were 1 away, and there were 2 that were 2 away. And the ones that were 2 away gave me n minus 2. So 5 minus 2 is 3. And then that told me, okay, so 2 plus 6, that means 8 is what I'm adding. And that's what we were adding there. So it's all about where do I stop here and what is n? So the farthest away that a point can be before you start getting close again, we're going to use the adjacentness is like the closest of the 2 distances. So we'll go ahead and use case 5 again. The farthest away it could be was 2. Well, if it was 3 away, then it went back to, oh, actually we're 2 away. So our adjacentness, when we had 5 total points on our circle, we kind of think about splitting it in half because of once I go over the halfway mark, I'll start getting closer again. So if I do n divided by 2, so in that case, 5 divided by 2 is 2.5. I just want to round down from there. So this function that I just drew, those symbols are called the floor function, which just means round down. So when I do the floor of 5 over 2, that is just 2. So my max adjacentness is 2 away. And that's also going to be true 1, 2, 3, 4, 5, 6. So let's make this one our new point. So again, if I take 6 and divide by 2, I'm going to get 3. And the farthest away, 3 rounded down, is just 3. The farthest away we get is 3. We also have to double some things. So there are two possible cases. If n is odd, then we double all of our points, right? So 1 away happens twice, 2 away happens twice. If n is even, then our farthest away one only happens once. So that 6 divided by 2 equals 3. We only count the third one once. So we can think about those 2 cases separately, but they're not going to be too different. So we'll start with the n is odd case first, and then we'll think about what happens when n is even. If n is odd, then I take my number of previous regions, and I'm going to use a summation notation to write out what we're doing. So this means is that we're going to add something up, and it has to do with our adjacentness. So we're going to start with an adjacentness of 1, and we're going to add up all the way until we hit that n over 2 floor. And what are we going to add up? We're going to add up what this formula gives me, because this formula generates each of these. So now what I want to show is that whatever this is going to be cubic. So if I can show that it's going to be cubic, then we're going to end up being, I'm going to end up being convinced that we are in fact a 4th degree pattern, and it's not just something that I notice in these first 8 terms. So the first thing that is important about adding a bunch of things up is it doesn't matter what order we do that in. If I do 3 plus 5 plus 7, that's the same thing as 3 plus 7 plus 5. So because the order doesn't matter, I don't have to do this first, get whatever that number is, and then add it to the next. So what that allows me to do is say, rather than figuring this out and then adding it to the next, keeping all of those things together, I'm going to figure out what I get when I add all of these up, and when I add all of these up, and when I add all of these up, and then I'll add all of that together. So what that means is we can break up this summation. So that means, still our previous one, we're going to break it up by the things that we're adding together. Oh, and I missed a step. We're going to have 2 times whatever we get because we need to do both the left half and the right half of our circle. So 2 times, go ahead and break up this sum. Okay, so I'm going to start with this one here on the end. So let's see what's going on there. So when we're adding up a bunch of 2's, that's all we're doing. We're adding up 2 plus 2 plus 2. And the amount of times that we're going to add 2 is going to be equal to the floor of n over 2. So like if I had this written, whoops, I'm adding up 2 3 times. That's the same thing as just 2 times 3. We can rewrite it with multiplication. And for sake of just making this more obvious and less annoying to write, I'm going to replace floor of n over 2. I'm just going to write m for that. So I don't have to write this. So this would just be the same thing as 2 times m. And that's a linear term. An important thing as we keep moving forward is this idea of when I add all these together, what am I going to get? Because again, I want to show this whole thing ends up being cubic that I'm adding. So an important thing is when I add polynomials together, so if I have something quadratic and I add something linear, oops, for example, I still end up with something quadratic. And if I add something cubic to something quadratic, I still end up with something cubic. So when we are combining polynomials, the type of polynomial we have just depends on what the highest degree was of the things we were added together. So as long as I have something cubic in here and nothing that's a higher degree than cubic, then we can be confident that we are adding something cubic every time. Those functions were just made up. They had nothing to do with the actual problem. It was just to illustrate this idea. So we know that we have a linear thing that we're adding. We want to hope that at least one of these is going to be something cubic. So let's go ahead and keep going. So now this time we're adding up a bunch of squared things. So in this case, it would look like a 1 squared plus 2 squared plus 3 squared plus m squared is what we're adding up. And sum of squares is actually a really neat pattern, and it is going to be something cubic. Um, there are some neat visual proofs about when you add up square things, you end up with something cubic. Um, it looks like this might be a nice explanation, so I'll go ahead and link that video in there. But I'm not going to get into the details. I will say just that when I have a sum of squares, that is going to be something cubic. So that is a good thing. We're going to keep going. What we want to show is that this part is either going to be quadratic or cubic. If it is or linear, just needs to be cubic or a smaller degree. So I'm going to go ahead and distribute n. So that's going to be, so an important thing about this situation here is that we actually treat n like a constant here. So a is something that is changing, but for this sum, only a is changing, not n. Okay, so I'm going to be able to then factor out this n since it's a constant. So this is the same sum as n pulled out to the side, a minus 1. And then just like we did when we broke this apart before, we can break this apart. So we're going to have n times the sum from a equals 1 to m of a minus the sum from a equals 1 to m of negative 1. And again, just like when we added up a bunch of 2's, adding up a bunch of negative 1's is going to give us something linear. In particular, this is going to be a minus negative 1 m times, which would be plus 1m when we cancel those out. When I add up a, so I'll use a dark green, I guess. This part is the same thing as 1 plus 2 plus 3 plus 4 plus m. We're just adding up m integers. This one is also a cool visual proof. These are called the triangular numbers. 1, and then 1 plus 2 gives you 3. 1 plus 2 plus 3 gives you 6. And the formula for that is going to give you something quadratic. So I'll go ahead and the formula for the triangular numbers is actually quadratic. So I'll go ahead and find a video at some point that shows that, or some other resource that shows it. But for now, for the sake of time, we're not going to get too into that. So just go ahead and believe me that that is. So this one is going to be quadratic. So kind of now we need to sum up literally all the things we have here. So we've got something linear, we've got something linear, we've got something quadratic, and we've got something cubic. When we add all of those things together and multiply by 2, we end up with something cubic. So we are in fact adding something cubic. So we can use our data to help us figure out a quartic, a fourth degree polynomial, that would model this situation, because now we can be confident that this pattern of adding something cubic every single time is going to continue holding true.
How I'm going to get my fourth degree polynomial is I know that a fourth degree polynomial looks like this. Let's see what happens if I use Desmos to fit this information. So I'm going to give Desmos our data here. Let's go ahead and zoom out so we can see our data here. Okay, so I'm going to have Desmos fit a fourth degree polynomial, and they've added this add regression button. I'm going to see if we can get, oh yeah, quadratic is a fourth degree polynomial. So here we go. We've got a function here, and I like that. I'm going to go ahead and change these fractions I'm going to change these decimals into fractions because I think that it probably is rounding a lot of them. I mean, these ones are obvious. So like here, it had a bunch of sixes and then went to a 7. This one, it had some 3s. I think those are going to be rounded decimals. Okay, so let's see if I remember how to convert a repeating decimal to a fraction. So we've got 0.958 and then 3 repeating. So 0.958, I'm going to break this up to that part's not repeating, but this is actually the same thing. If I have 3 zeros here, that means I took 0.3 repeating and I divided by 1,000, and I still have that 0.958 over here. So, and I know 0.3 repeating is 1/3. So this is 958 over 1,000. That's 958 thousandths is what that decimal is. This decimal, oops, not equals. And then we have our 1 over 1,000 times 0.3 repeating is the same thing as 1/3. So we have 958 over 1,000 plus 1 over 3,000. Common denominator is 3,000 there, so let's take 958 times 3. With a calculator, I got that's 2,874 over 3,000 plus 1 over 3,000. So that's going to be 2,875 over 3,000 is our fraction there. So I'm going to replace this one with 2,875 over 3,000. Let's do our next one. Also, 125 over 3,000, both of those can be divided by 5. So let's reduce. What's 125 divided by 5? Hold up, I'm going to write it over here. So 125 over 3,000. And if I divide that by 5, that's 25. 3,000 divided by 5 is 600. We can divide both of those by 5. 5 divided by 5 is, 25 divided by 5 is 5. 600 divided by 5 is 120. 120 divided by 5. Okay, so that's 1 over 24. Okay, let's reduce our other fraction. Okay, so there we go. That is the function that I would trust. So this tells me that if there's 100 points on the circle, there's going to be 3,926,176 regions. If you would like to see some strategies for figuring out this formula yourself, I will make a different video that does just that.